Hey everybody, today's lesson from Unit 2.2 is all about the angle-angle similarity postulate. It's a shortcut, or a way to prove that triangles are similar without comparing all three pairs of corresponding angles and without comparing all three pairs of corresponding sides. But to get to the angle-angle shortcut, we're first going to do a little observation. So if you would take your ruler and create two line segments, and we're going to name them line segment AB and line segment A prime B prime. So I don't have a ruler that I could use on here, so if you just take a look, I'm going to call this my line segment from A to B, and this will be my line segment from A prime to B prime. And the line segment connecting A prime and B prime should be a little bit bigger than AB. Okay, next you're going to take your protractor and create an angle here at point A. And I'm going to create an angle that's about 40 degrees. So if I had my protractor, I would measure it, mark it off as 40 degrees. And then you're going to do the same thing down here at A prime. Now, don't worry about the segments that you drew, just worry about getting the angles to be congruent. Do the same thing at your point B and point B prime. So I'm going to pick a different number. I'm going to measure 30 degrees. And I'll do 30 degrees down here as well. Okay. And if you take a look, those two triangles have two pairs of corresponding angles that are congruent. And the third angle in each triangle would be 110 degrees. Okay, next you're going to take your ruler and we're going to measure each pair of corresponding sides. So this point is going to be point C, this will be point C prime. So now we're going to go with measurements that I have on my written notes and not what appears here on the screen. Okay. So on my written notes, I measured this to be line segment from A to B to be 5 centimeters. And my A prime B prime was about 8 centimeters. So that would fill in this first ratio as 5/8. And we're going to compare these ratios as decimals. So I'm going to take a calculator. Finally, we get to use calculators. And 5 divided by 8 as a decimal is 0.625. Okay, next we're going to take a look at BC and B prime C prime. BC in my picture was 3.4 centimeters and B prime C prime was 5.5. So when we compare 3.4 to 5.5, and you'll do the same with your picture, remember your measurements are going to be different. When I divided those out, I got the decimal 0.618. Finally, for AC, I had a measurement of 2.6 centimeters, and A prime C prime was 4.3. And when I compare those, I have 2.6 divided by 4.3. It works out to be approximately 0.604. Now, they're not exactly the same, and that could be because I measured quickly, okay, or my use of the protractor might have been off a little bit. But are the ratios approximately the same? Yes, they are. Okay, so that shows that all three pairs of corresponding sides are proportional, and we know that all three pairs of corresponding angles are congruent. So it does mean that our two triangles are similar to each other. So I'm going to scoot this up and write that similarity statement. Okay, so we're going to say triangle ABC is similar to triangle A prime, B prime, C prime. Now what this little demonstration shows us is that we don't have to go through and measure everything and find all three angles. It's enough to know that two pairs of corresponding angles are congruent. That's enough for us to determine that the two triangles are similar. So our AA similarity postulate states if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. Be careful, you're going to want to say that they're congruent. We're not proving triangles congruent. They're definitely not congruent, but they are similar to one another. Okay, in our first example, it says use the diagram to complete each statement. Well, first, in part A, it's asking us to determine if these two triangles are similar to each other. So we want to say triangle ABC is similar to what other triangle. So use your diagram, take a look at the markings. We're told that AB is parallel to DE. So that means that we have parallel lines being cut by a transversal. We should know what that gives us. That's going to give us a pair of alternate interior angles that are congruent here, and another pair of alternate interior angles that are congruent here. Because if two parallel lines are cut by a transversal, then alternate interior angles are congruent. Okay, that's enough for us to say that these two triangles are similar. Just be careful on how you name them. So the first triangle is named triangle ABC. We're going to name the second triangle so that the corresponding angles are congruent. Notice angle E is marked congruent to angle A. So our second triangle name is going to start with E, go to D, and then into C. Okay, so triangle ABC is similar to triangle EDC. In part B, we have to set up the ratios of the corresponding sides. So side AB corresponds to ED, side BC corresponds to DC, and side AC corresponds to side EC. In part C, we're asked angle B is congruent to what angle? And it's congruent to angle D. You can tell from our markings on the diagram, or you can look at how we name the two triangles. In part D, we're setting up some proportions. So this side length of 4, which is how AC is labeled, that corresponds to EC. So EC is equal to 6. So we're going to have 4 over 6 equals what over 12? Well, here's the 12, and it looks like the side that corresponds to DE is line segment AB. So we're going to fill this in with x over 12. And what we have here is a proportion that then we can solve for x. So we have 4 over 6 equals x over 12. Reduce that to 2/3 equals x over 12. Cross multiply, we get 3x equals 24, or x equals 8 when we solve it. Now notice this, that 4 over 6 reduced to 2/3, that's our scale factor. Okay, use that scale factor of 2 over 3 to solve for y. So check out where y is. Y is the length of DC in here. So that's going to go in the denominator. And BC is the segment that corresponds to that. I'm using this ratio right here. So BC is 6, and it corresponds to DC, which is y, and that's equal to our scale factor. So cross multiply, you get 2y is equal to 18, or y is simply equal to 9. Now, we have two really nice answers here, no fractions, no decimals, but just to give you a heads up, we may find that our answers are fractions and decimals, and that's okay. Okay, in the next example, it says determine whether the triangles are similar. If they are, write a similarity statement. A similarity statement says triangle so-and-so is similar to triangle so-and-so. All right, so make sure you take a second to write that. Okay, so proving the triangles similar to one another, we have to find two pairs of corresponding angles that are congruent. In part A, recall that we can find the third angle in a triangle. If we add up the two that we already know, 90 plus 50 would be 140. Subtract it from 180, because the total of the three angles in a triangle is always 180. And that's going to give us 40. Now check it out. Angle G is congruent to angle J, and I and K are congruent because they're both right angles. So we can make the conclusion that triangle HGI is similar to triangle LJK. Just watch the order in which you name everything. Okay, in part B, we're using parallel lines here. So parallel lines being cut by this transversal on the left leaves us with corresponding angles that are congruent. You can also use the corresponding angles that appear on the right-hand side of those two line segments, or you can even go with a shared angle that both triangles use. And no matter which way you look at it, the two triangles are similar to one another. So I can say that triangle JNL, that's the big triangle, is similar to triangle KML. Again, these pairs of triangles are similar by the angle-angle similarity. So this one was a yes, this one was a yes. Okay, in our third triangle set here in part C, we do see the right angles, so that's one pair of angles that are congruent, so we're halfway there. And then if you take a look at this little triangle SQR, it shares this angle R with a big triangle, so that's our second pair of angles that are congruent. So we can say for sure that these two triangles are similar, and we're going to say triangle OPR is similar to, now just be careful, and when you name the second triangle it has to be named triangle QSR. Again, the corresponding angles must be congruent, so just watch out when you go to name them. One of the most common practical applications of similar triangles is to find the height of an object that otherwise would be really hard to measure. It's called indirect height. So in this example, Kim wants to find the height of a certain tree for a report for her biology class. Her method used shadows as shown in the diagram below. She measured the shadow of a tree and found it was 5 meters long. She measured her shadow and found it was 0.8 meters long. So here's what's going on. The sun up in the sky casts a shadow after it hits an object. So the tree's shadow is this segment from S to T, and it's 5 meters long. And Kim is standing close to the tree, but not right next to it. And she's standing so that the tip of her shadow matches or coincides with the shadow of the tree, the tip of the tree's shadow right here. She lined it up. And her shadow is 0.8 meters long. Now Kim's height is 1.6 meters, and the tree's height is the part that we don't know. Okay, so it says name the similar triangles in the figure. We'll notice that both triangles have a right angle, so we have one pair of angles that are congruent. Also notice that the triangles overlap and share angle S in common, so that's our second pair of angles that are congruent. So by the angle-angle similarity postulate, we can say that triangle HSC is similar to triangle RST. Now part B is what we can take away from that. Now we can write the proportion. SC corresponds to ST in the same way that CH corresponds to TR. So if Kim is 1.6 meters tall, how tall is the tree? So we're going to plug in what we know. SC is equal to 0.8 meters. ST is equal to 5. So that's the length of Kim's shadow as it compares to the length of the tree's shadow. And that ratio will be equivalent to Kim's height, which is CH, or 1.6 meters, compared to the height of the tree. That's TR, but we're just going to call it H to make it a little bit easier. Okay, cross multiply to solve the proportion. We get 0.8H is equal to 5 times 1.6. So we have 0.8H is equal to 8.0. And when you divide by 0.8, we get the height is equal to 10 meters. So again, indirect height. That means we're solving for a height that's hard to measure. So in this case, our use of similar triangles helps us out. Okay, good luck on the CYU and the homework. Please ask if you have questions.